So, back in 2017, a handful of researchers at Google dropped a paper with a pretty bold title. And you know what? They weren't just suggesting a small tweak. They were proposing a complete rewrite of how we do things. And it's what unleashed the generative AI we see all around us today. Okay, let's grab our notebooks and sketch out the paper that really changed the game. Attention is all you need. Right out of the gate, the authors make this claim that at the time was just audacious. They were essentially saying, you know those two big methods everyone uses for language, recurrence and convolutions? Yeah, we're throwing them out. They wanted to replace them with just one single, powerful idea. To really get why this was so revolutionary, we have to rewind and look at how AI understood language before this paper came along. See, the problem was this major bottleneck in how the models could even think. Imagine you're reading a long sentence. You have to read the first word, then the second, then the third, right? In that order. Well, that's exactly how the top models of the day, things called recurrent neural networks, or RNNs, had to work. They were forced to process everything in a line, one piece at a time. And that created some huge problems. Because everything had to be in order, you couldn't do the work in parallel, you couldn't just look at the whole sentence at once, you had to wait for word one to finish before you could even start on word two. This made training these models incredibly slow. But even worse, it meant the model had a terrible memory. By the time it got to the end of a long paragraph, it had basically forgotten what the beginning was about. The connection was just lost. So the authors of this paper asked a brilliant question. What if we could just get rid of the line? What if a model could look at every single word in a sentence at the exact same time and decide for itself which words were the most important to understanding all the others? And that is the absolute core idea of self-attention. It's this mechanism that lets the model, for every single word it's looking at, calculate an attention score for every other word in the sentence. It learns context by figuring out which words are most relevant to each other, no matter how far apart they are. So how in the world did they build a machine that could actually do this? Let's sketch out the architecture of this new model they created, which they called the transformer. Okay, at its heart, the transformer has kind of a two-part brain. First up is the encoder. Its only job is to read the input sentence, let's say in English, and just understand it. It creates this really rich mathematical representation of what it means. Then it passes that pure understanding over to the decoder. And the decoder's job is to take that meaning and generate the output, word by word, in another language, like French. And here it is, the full blueprint from the paper. Now, don't let it intimidate you. Over on the left, you see the encoder stack, and on the right, the decoder stack. You'll notice they're both just made of identical layers stacked up, but the real magic, the secret sauce, is happening inside those boxes labeled multi-head attention. Now, this is where it gets really clever. The model doesn't just figure out attention once. It does it multiple times, all in parallel, using something called multi-head attention. Think of it like you have a whole team of specialists all reading the same sentence at once. One head might be a grammar expert, linking adjectives to nouns. Another head might be focused on the action, connecting the verb to the subject. By combining all these different points of view, the model gets a much, much richer understanding of the sentence. And each one of those heads is powered by this one core mechanism, scaled dot product attention. I know it looks a little complicated, but the idea behind it is actually pretty simple. It all comes down to three things the model learns for each word: a query, a key, and a value. Here's the best way to think about it. Imagine you're in a library, and every book is a word in our sentence. For the word we're currently focused on, it sends out a librarian. That's the query. The librarian has a specific topic it's researching. Now, every other book in the library has a label on its spine. That's the key. The librarian runs around comparing its topic to all the labels to see which books are the most relevant. The better the match, the more attention it pays. Finally, the librarian grabs the contents of the most relevant books, those are the values, and blends them all together into one perfect summary. So the model literally learns how to ask the right questions to find the right information. Okay, so you might be wondering, if the model is looking at all the words at the same time, how on earth does it know what order they're in? That's a great question. The transformer solves this by adding a special piece of information to each word called a positional encoding. It uses this clever mix of sine and cosine waves to give each word a unique signal, almost like a GPS coordinate, that tells the model exactly where it is in the sequence. So, the theory was brilliant. It was elegant. But Did it actually work? Well, the answer was a massive, resounding yes. And it wasn't just a small step forward, it was a huge breakthrough for the whole field. This little table from the paper explains exactly why. Look at that last column, max path length. For an old school recurrent network, the distance for information to travel from the first word to the last word is n, the length of the sentence. But for self-attention, the distance is O1. It's constant. It's like having a direct phone line between every single word and every other word. That makes learning those long-range connections way, way easier. So, when the authors put the transformer to the test on real-world translation tasks, the results weren't just good, they were completely off the charts. They didn't just move the goalposts, they built a whole new stadium. On the standard English to German translation test, the transformer got a BLE score of 28.4. Now, that number by itself doesn't mean much, but get this. That score wasn't just better than any other single model at the time, it actually beat entire ensembles. That's whole teams of models that were bundled together. And for English to French, it set a new record for a single model at 41.0. Maybe the most impressive part? It did all of this while training way faster and cheaper than the old models. We're talking just 3.5 days on 8 GPUs, a tiny fraction of the cost of its predecessors. The legacy of this one paper is just staggering. It didn't just set a new record, it laid the entire foundation for the modern AI revolution. The transformer architecture is the direct ancestor of pretty much everything you've heard of. BERT, which changed how search engines work, and of course the GPT models that power the tools we use every day. This wasn't just an update, it was the spark. So, as we look back at our notebook here, what are the big takeaways? First, the transformer kicked slow, one-word-at-a-time models to the curb and brought in a parallel design. Second, it used self-attention to look at all the words at once, completely changing how AI understands context. Third, it just smashed the old records for both speed and quality. And finally, and most importantly, it gave us the blueprint for the AI that is literally changing our world right now. By swapping out that slow, sequential process for pure attention, this paper gave AI a genuine superpower, the ability to understand context on a global scale. The question it leaves us with is, now that this power is out in the world, what are we going to build with it next?